Welcome friends and welcome to my series of video lectures on design of RCC structures. We are in chapter 2, Flexural analysis and design of singly reinforced rectangular beams. The title of this video lecture is RCC 2.6 Numerical Problems on Flexural Analysis. For best video quality, watch this video on laptop or desktop with resolution set to 1080p HD. The expected learning outcomes from this video lecture are 1. To determine ultimate moment of resistance of given beam. 2nd. To determine ultimate load carrying capacity of given beam. The contents of this video lecture are 1. Numerical problem 2.6.1 on simply supported beam, and second, numerical problem 2.6.2 on cantilever beam. We are going to use some key terms in this video. So, moment of resistance, load carrying capacity, balanced section, under reinforced, over reinforced, cantilever, neutral axis, ultimate load. Friends, we have our best friend Smarty with us with some tips. Write down your own notes while watching the video. Pause or rewind the video whenever required. Do solve the formative and summative assessment quizzes even in the video. Friends, we are studying now numerical problems on flexural analysis of beams. And this is problem 2.6.1. Let us read the statement of the problem. A rectangular RCC beam has effective cross section as 230 mm by 550 mm. It carries a bottom reinforcement as 3 bars of 20 mm diameter. Materials of grades M25 Fe500 are used. Span of beam is 5.6 meters. Simply supported. Determine A. Ultimate tensile and compressive forces of resistance. B. Ultimate lever arm. C. Ultimate moment of resistance. D. Ultimate and working load carrying capacity of beam. Friends, we can see an example of simply supported beams in RCC building here. Here we see some columns and we see these beams. So we can assume these beams to be simply supported over these columns. So this is the beam 1, 2, 3, 4, 5, 6. So there are 6 beams of the type which we are studying in this problem. Now let us go for the solution of the problem. Let us draw the diagram first and let us study the diagram. It is given in the problem that it is a simply supported beam. So we can see this beam as a simply supported beam. So beam type is simply supported. Second, it is having dimensions or cross section as 230 mm by 550 mm. We have to note that it is given to be an effective cross section. We know that there are 2 types of cross section or 2 ways in which we can give the dimensions. One is called the overall or total dimensions, the other is called as effective dimensions. So here the dimensions are given effective. What is its significance? In the diagram we can see that B is 230 mm and this 550 mm is D, which is effective depth. What is the meaning of effective depth? It is the depth from the top of the beam up to the center of the reinforcement bars. So that is the effective depth. Overall depth starts from the top of the beam and ends at the bottom of the beam. So this is the difference. So in this problem it is directly given as effective depth. We are required to use the effective depth only for calculations. So in this problem that is readily given. Now next thing is it carries bottom reinforcement as 3 bars of 20 mm diameter. So it is clearly mentioned that the reinforcement is provided at the bottom. So here we see three bottom bars. So there are three bars of 20 mm diameter. Now these three bars, their total area will amount to 942 mm square, as you can see here. AST is equal to 3 bars, so 3 into area of one bar is pi by 4 into 20 square, because every bar is 20 mm in diameter. So the total cross sectional area of steel is this, and which amounts to 942 mm square. So here we see 942 mm square. Now the material grades are M25 Fe500, that is given. Now what is the meaning, what is the significance of these material grades? One significance is that we get the value of design constant KUB. KUB is neutral axis constant, which we will be using in our problems. So this KUB value is 0.46 for this combination of materials. In the earlier videos, we have seen the meaning and significance and method of calculation of these design constants, out of which this is KUB and it is 0.46. We have to remember the values of these constants, otherwise we have to spend extra time in deriving them from the formula. Now we can see this diagram. We know that whenever there is a flexural action, structural action, the beam gets divided into two zones. One is the compression zone, the other is the tensile zone. Now the type of bending in case of a simply supported beam is sagging. You know what is the meaning? The sagging is the shape like this. Okay, so if it is a sagging shape, we get tension zone at the bottom of the beam and compression zone on the top side of the beam, and the two zones are separated by a layer called as neutral layer. So this blue, green line indicates the neutral layer. That same neutral layer, which is called neutral layer in this section, in the longitudinal section, is called neutral axis in the cross section of the beam. Now we can see that we have taken cross section AA here. Now this cross section AA is a critical section. That means it is the section at which bending moment will be maximum. So we are talking about this cross section of the critical section AA. Here we see the typical bending moment diagram of the simply supported beam carrying the UDL. Here we see the WU as the ultimate UDL applied to the beam. So we get maximum bending moment MU max equal to WL square by 8. Now here we see the stress diagram. The stress diagram consists of two internal forces of resistance, CU and TU. So CU, capital CU and capital TU, these are the two internal forces of resistance. CU is generated by concrete, which is compressive force. TU is generated by steel reinforcement, which is tensile force. You can see that this TU is shown directly opposite to the reinforcement bar. Okay, whereas the CU is shown at a distance 0.42 XU, at a depth 0.42 XU from the top. We know that the stresses of resistance in concrete are distributed over this much total area, and that is the distribution of stress is parabolic and rectangular like this, which is directly derived from the stress strength graph of concrete, and that is why we get this CU acting at 0.42 XU. So this is the CU, this is the TU, these are the formulae for that. Now we will start solving the problem. So step 1 is calculation of XU. XU is the depth of neutral axis. Depth means the distance from the top, and the distance of the top from of the neutral axis, this is XU. Now how to calculate XU? We know that the internal forces CU and TU, the internal resisting forces CU and TU, they form a couple, and that couple counteracts with this MU max couple, which is from outside. So this is bending moment and this is moment of resistance. So it is a comparison of two couples, MU max and MUR. So if MU max is the couple which is acting in the form of bending moment from outside due to load, whereas MUR is the moment of resistance, that is the couple that is resisting this bending moment. So let us have a clear glance or clear view that this MUR is resisting couple and MU max is acting couple. Now we have to calculate in this problem value of MUR and the further things. Now since this CU and TU are forming a couple, they are equal. So we start our step 1 as calculation of XU. For this calculation of XU, we have to assume initially that the section is under reinforced, and then we can use this equation CU equal to TU. So CU equal to TU gives us this equation. What is CU? You can see CU is 0.36 FCK BXU. This analysis we have already studied when we derived the formula for ultimate moment of resistance in the earlier video. So you can refer to the derivation in that video. Here we are directly using those values. So CU is 0.36 FCK BXU and TU is 0.87 FYASP. If we simply put the values, it's easy to put the values. We can see 0.36 into FCK is 25. FCK is the grade of concrete, FCK M25, 230 is the breadth of the beam, and XU is to be found out, so it will be kept as it is. This is equal to 0.87, Fy is this 500 which is grade of steel, Fe 500, into AST, this is 942 mm square, you can see. So once we substitute the values, we get the answer as XU equal to 197.96 mm. So you can show it here, 197.96 mm. There is a very practical advantage of writing all these values back in the diagram so that we get a clear visual idea of what is going on in the numerical problem. Now we will proceed for step 2 in the next slide. Friends, we now continue with step 2 of the same problem which we are discussing, problem 2.6.1. In step 1, we have got the answer as the depth of neutral axis XU is 197.96 as shown here. Now we move for step 2. Step 2 is a question, is the section under reinforced? We have assumed that CU is equal to TU based on the section is under reinforced in step 1. So we have to now check that assumption. For that, we have to calculate depth of balanced neutral axis XUB. This beam which we are studying it may be under reinforced, over reinforced or balanced. We calculated this XU by assuming that it is under reinforced. Now it is the time to check it. Now we have to check it by comparing this XU with another value XUB. That XUB is the depth of balanced neutral axis. That means it will be the depth of neutral axis if the beam were a balanced beam. So in the earlier videos we have seen how to use the design constants and how to calculate them to calculate the properties of balanced section. So here we will calculate depth of balanced neutral axis XUB by the small formula XUB equal to KUB into D. Now in the earlier slide we have seen for the materials M25 Fe 500 we have got the value of KUB as 0.46. So we use that value here. So this is 0.46 into 550, this gives 253 mm. So if this beam was a balanced beam, its depth of neutral axis would be 253 mm. But it is actually 197.96 mm. So it is clear that the beam is not a balanced beam. So whether it is under reinforced or over reinforced, that is to be checked now. Then if you get this XU less than this XUB, if this is 197.96 and this is 253, so XU is less than XUB. So as XU is less than XUB, then this indicates that the beam is under reinforced. If XU is greater than XUB, in that case the beam becomes over reinforced. So in this problem, XU is 197.96 and XUB is 253. So XU is less than XUB, hence the section is under reinforced. So whatever assumption we made while calculating XU in step 1, that the beam is under reinforced, that assumption holds good here, and that is why we can confirm value of XU as 197.96 as calculated in step 1. So the purpose of step 2 was to confirm the value of XU calculated in step 1. Now we proceed for the third step. The step 3 is calculation of CU, TU, ZU and MUR. These are the 4 things asked in the problem. So let us go one by one. They have asked in part A, ultimate tensile and compressive forces of resistance. We know that this CU and TU, they are the forces of resistance and they form a couple, and the couple is having a lever arm, that is the perpendicular distance is as ZU. So this is the internal couple of resistance, whereas this is the external bending moment MU max. So problem of flexural analysis is nothing but the comparison of external action, that is MU max, the bending moment, and the internal resistance, that is the MUR or ultimate moment of resistance. So let us start calculating the 4 values. So ultimate compressive force is capital CU. As we can see, the formula is here, 0.36 FCK XU. So just put the values. 0.36 into FCK is 25 for concrete M25, 230 is the breadth of the section B, and 197.96 is the depth of neutral axis as confirmed here. So this will amount to 409.78 kilonewton. So we will say that the concrete had generated an internal force of resistance of CU equal to 409.78 kilonewton. Now TU, capital TU is the force of resistance generated by steel. This is what the steel is doing in the beam, that it is generating a force of TU. So that is calculated as 0.87 into 500, which is Fy, grade of steel, and AST is area of steel, the 3 bars, that is 942. You will find on calculation that this value is also 409.78, exactly the same as TU. So whatever we are saying that the CU and TU form a couple of resistance. So that couple means 2 equal and opposite and parallel forces. So the CU and TU automatically they become equal. You can observe. Now this was the second value. Now third value is ZU. ZU is the lever arm. Lever arm is the perpendicular distance between the 2 parallel forces in a couple. So this is ZU. Now you can see this easily derived formula, that this ZU, this distance is total distance, that is effective depth D minus 0.42 XU is the distance at which this force CU is acting. The force CU is acting at this distance from the top. The details of the stress block and its properties we have already studied in another video, so I am not emphasizing any more points in that. So we get this ZU or lever arm as D minus 0.42 XU. So D minus 0.42 XU, D is effective depth 500 minus 0.42 into XU is 197.96. So we get this value as the amount of lever arm, right? 466.86 mm. Now the last thing is ultimate moment of resistance. So we will calculate the ultimate moment of resistance MUR equal to CU ZU, which is CU is 409.78, you can see 409.78 into ZU is 466.86 as calculated here. So just do the calculation and you get this final answer. You get this answer in kilonewton mm, and finally you convert it into kilonewton meter as 191.31 kilonewton meter. So that is the ultimate moment of resistance of this beam. So this beam can generate with this cross section and this area of steel. This beam is an under reinforced beam and it can generate an internal moment of resistance as 191.31 kilonewton meter. So now in the last step we will calculate how much load this beam will be able to bear safely. So if it is able to resist a bending moment from inside of this much, then how much load should we apply to the beam so that it can remain safe. So it is the last step, calculation of load carrying capacity. So the load carrying capacity is calculated by equating this MUR to MU max. So let us assume that the beam is subjected to its maximum load, which is equal to the capacity of the beam to resist bending moment, and that is why we say MUR equal to MU max. We know for MU max means maximum bending moment for simply supported beam with UDL. We know that the formula for maximum bending moment is WL square by 8. So this is the bending moment diagram, which is a sagging bending moment positive diagram, and it's a parabolic curve, and we get the peak point at this center. That is why we are treating this section AA as the critical section. So we do this calculation here. MUR equal to MU max. MUR is calculated as 191.31 is equal to WU we want to calculate into 5.6 is the span of the beam. 5.6 is the span of the beam as given. So upon 8, so this amounts to WU equal to 48.8 kilonewton per meter. So this UDL that we have shown, this value of WU is supposed to be 48.8. So you can apply a maximum ultimate load of 48.8 so that it will be able to the beam will be able to resist it safely. Now we know that the ultimate load is to be further reduced to the working load. We design the beams for ultimate load, but ultimate load is not the load actually which we are supposed to apply to the beam. So that load is called as working load. We know that working load W is calculated by WU upon gamma F. This gamma F is partial safety factor for load. We have studied in detail the meaning and concept and values of partial safety factors for loads and materials in the earlier video. So, and there we have seen that this gamma F, which is the partial safety factor for load, is having value 1.5. It is also called as load factor. This is directly given in IS 456-2000. So we get 48.8 this WU upon 1.5, 32.53 kilonewton per meter. So practically you can apply a load of 32.53 kilonewton to the beam so that it will be safe. So this was the fourth and D, this fourth value expected, ultimate and working load carrying capacity of the beam. So finally let us just consolidate all the answers at a glance. So these are the answers. CU, TU both are 409.78 kilonewton, ZU is 466.86 mm, MUR is 191.31 kilonewton meter, WU 48.8 kilonewton per meter, W 32.53 kilonewton per meter. So friends, here we come to the end of this problem, and this was a problem on a simply supported beam subjected to uniformly distributed load. We will continue with problem 2. Friends, now we will move to problem 2.6.2. I will read the statement of the problem. A rectangular RCC cantilever beam with overall cross section as 230 mm by 350 mm carries a tensile reinforcement as 3 bars of 22 mm diameter. Materials of grades M25 Fe415 are used. Span of the beam is 1.4 meters. Determine ultimate and working load carrying capacity of the beam. So this second problem on flexural analysis will make the ideas and concepts quite clear. Let us first see this field example. We can see from the statement of the problem that this problem is based on cantilever beam. So here we see a field example of a cantilever beam. We know that a cantilever beam is a beam which is supported only on one side on a column, and that support is a fixed support and the other end is free. There is no other support for the beam. So here we see this column, here we see this cantilever beam projecting up freely from this column, and at the top of the beam we see a slab which is supported by that cantilever beam. So here slab is supported by this cantilever beam and this cantilever beam is supported on the column, and this is a field example. Now we will solve this problem step by step. So solution. First of all, we will convert the statement of the problem into a diagram, and then we will have diagram and problem interpretation. So let us interpret the statement of the problem with the help of this diagram. So it is a cantilever beam, first thing. So here we are showing a column and we are showing a beam projecting out. There is no support on the other side. Now whenever we are saying that it is a cantilever beam, we have to immediately remember that its bending pattern will be of hogging type. It will deflect like this, right? It will deflect like this, and that is why we will get a hogging bending moment. A hogging bending moment will further give us that the tension zone of the beam will go at the top. So here you will see the tension zone, as you will read here. Tension zone has gone at the top and compression zone is at the bottom. This is exactly reverse of the simply supported beam in the earlier problem. That is why we are taking this problem. So there is a neutral layer, there is a neutral axis, all the rest of the things are the same, but the things are inverted. So we get this tension zone at the top and compression zone at the bottom. Now we know that in RCC we are providing the steel reinforcement where there is tension zone. So in case of a cantilever beam, we will have to provide the steel bars at the top. So in the problem it is said that the tensile reinforcement has 3 bars of 22 mm diameter. They are not mentioning whether this reinforcement is provided at the top or at the bottom. They have left it to us. So we have to understand that it is to be tensile reinforcement. So it will go in the tension zone. So it will go at the top of the beam. So now when it is particularly a cantilever type of beam, the reinforcement does not end here. It penetrates into the column for some distance with an L bend. So this is a reinforcement, typical reinforcement detailing for only a cantilever beam. This length which projects inside we call as anchorage length. Later on we will study the details of this, but in order to have a realistic diagram, I have shown that the bar is going here and going back bent inside the column. So this is the steel reinforcement. Now this steel reinforcement is consisting of 3 bars as given here. The tensile reinforcement has 3 bars of 22 mm diameter. So if you calculate the area of 3 bars, it will amount to 3 into pi by 4 into 22 square, 1140 mm square. So that is the AST, area of steel in tension. Now one more important difference in this problem as compared to the earlier problem is that overall cross section is given. In the earlier problem, effective cross section was given. Now when overall cross section is given, it means that this 230 by 350 are the total dimensions. You can see this B is 230, it is the same, but D is capital D, not small d. This is capital D equal to 350 mm, which starts from the bottom of the beam up to the top of the beam, total, right? So this makes us calculate additional value, which is the effective depth of the beam. So the effective depth of the beam is not directly given, overall or total depth is given. So from the effective depth we have to calculate the overall depth, we have to calculate the effective depth. For that we will use this small. We have already studied this concept of effective depth and overall depth. I have just highlighted and enlarged this portion. You can assume this bar as this bar and you can see the distances. Okay. So effective depth, you can see here, overall depth capital D is 350 mm. This gives us effective cover and effective depth. What is the formula for effective depth? Small d is capital D minus d dash t. What is this d dash t? D dash t is effective cover. You can see here d dash t. Now how this d dash t is calculated, we will see here. This is the effective, this is the bar, this is the top of the beam, and this is the edge of the beam. This is the bar, rebar of diameter phi, and then this is d dash t, which is clear cover of the bar. What is clear cover of the bar? Clear cover is the distance from the amount of concrete which is laid outside the bar. So this is d dash tc. D dash tc is the effective cover, a clear cover. So clear cover plus half the bar diameter, so effective cover. What is effective cover? Effective cover is the distance of center of the bar from the extreme end. So distance of center of bar from the end of the beam. Now, so this is d dash t as d dash tc plus phi by 2. So we have to remember this formula. Effective cover d dash t is d dash tc, which is effective clear cover. C stands for clear plus phi by 2. So we get this effective cover as d dash t equal to d dash tc plus phi by 2. Now here it is mentioned for beams, d dash tc, that is the clear cover for beams, is given as 25 mm by the IS 456-2000. We have already covered in an earlier video the concept of effective and clear cover and so on. So this is 25 clear cover plus 11 is 22 upon 2, that is 22 is bar diameter, so that is 25 plus 11, this amounts to 36 mm. So the total depth is given to be 350 mm, but it is to be reduced by 36 mm, and you will get effective depth as 350 minus 36 as 314 mm. So this is 314. Now what is this depth? It is from the end of the beam up to the center of the reinforcement, right? So this is small d. So difference between effective cover, effective depth and overall depth is required to be used here. So this was a small calculation required in the problem because overall dimensions are given. Now after this, what is asked, what is to be calculated? Well, they have asked us to calculate ultimate load carrying capacity and working load carrying capacity. They are not asking intermediate details, but we will have to calculate them. Now the type of problem is analysis type problem. This is an analysis type problem. Now because this beam is looking inverted, you will see this diagram also inverted. This concrete stress block will come down. The tensile force Tu will go up, Cu will. There is nothing new, nothing different in this. Only thing is that the picture is presented in an inverted form. So this is looking somewhat different, but the basic concept and every other numerical details are the same. We are taking this problem just to make us familiar with any type of situation which we are likely to come across. So let us go on and start solving the numerical problem. The steps are exactly the same as they were in the previous problem. Step 1 is calculation of XU. Assuming that the section is under reinforced, we are using the formula Cu equal to Tu. Here again you see this Cu and Tu. They are the same. The formulae are the same. So Cu equal to Tu. Cu is 0.36 FCK BXU. You can see here. That is equal to 0.87 FYAST. This is there. So you simply put the values. Here the grades of steel and concrete are M25 concrete and Fe415 steel. Fe415 steel. So 1140 mm square is the area of steel. So if you just substitute the values, you will get XU as 198.84. 198.84 is the value of depth of neutral axis as calculated from step 1. Now we will continue with step 2 in the next slide. So continuing the same problem, we have calculated from step 1 that the depth of neutral axis XU is 198.84 mm. Now as in the earlier problem, we will go for step 2 as is the section under reinforced? We have calculated this XU by assuming that the section is under reinforced. Now in this step 2 we will check whether it is under reinforced. For that we will compare this value of XU with the value XUB. XUB is depth of balanced neutral axis, which is calculated by the formula KUB into D. Now KUB for the materials M25 Fe415 are it is having the value 0.48. So 0.48 into 314 is the effective depth, as we can see here, effective depth, and this amounts to 150.72 mm. This means that if this beam, whatever beam we are talking about, if this beam has to be balanced, then it should have XU as 150.72. Whereas we find here that XU is 198.84. This means that XU and XUB are not equal, which means that the beam is not balanced. Now the question is whether it is under reinforced or over reinforced. Now if you just compare the two values, you will find that XU is greater than XUB. This is different as compared to the earlier problem. So as XU is greater than XUB, the section is over reinforced. Section is over reinforced. Now when the section is over reinforced, we cannot confirm the value of XU as this, because here the assumption gets violated. Assumption in step 1 is violated because the value is XU is greater than XUB. IS 456-2000 is not allowing us over reinforced sections, as we know. So what maximum we can do is we can assume this section to be balanced, but not more than that. So for that we will have to make a correction in the value of XU. So we cannot take this value of XU as 198.84 because the section happens to be over reinforced. So we will have to restrict the value of XU to XUB, that is 150.72. We cannot take it 198, we have to restrict it to 150.72. So here we are not saying to confirm the value of XU, no, we are taking the value XU equal to XUB equal to 150.72 mm. So this is how we take the value of XU in the step 2 when the section is over reinforced. Now we will do all the further calculations with the same formulae, but with the value of XU as 150.72 mm. So step 3 is again the same, calculation of MUR. Here they have not asked the values of CU, TU, ZU. So we are not calculating those values. We are directly calculating the value of MUR. So here for over reinforced section, due to correction in the value of XU, we have seen here that the value of XU has been corrected here. It has been changed from the earlier value. So due to this correction, if we calculate the value of CU as well as TU, you will find that they will not be equal. CU will come out to be less than TU, and in that case we should use the lower value to calculate MUR, and that is why we will use the formula for MUR as CU into ZU and not TU into ZU. So MUR is CU into ZU. So this is equal to CU, you put the entire value 0.36 FCKB XU, and you put the value of ZU. You can just see the formula here. So D minus 0.42 XU. So if we just put all the values here, 0.36 FCKB into XU, you can see XU as 150.72, the corrected value. D is 314 small d minus 0.42 XU. So this comes out as 78.21 kilonewton meter. So this is the MUR of the beam. So this MUR is 78.21 kilonewton meter. After that, step 4 is the last step. So that step is if your MUR is 78.21, how much it should be this UDL? You just tell us how much UDL should be applied if that MUR is this much. So what we do is we equate this MUR to this MU max value. We can see here this is a Hogging bending moment diagram. This is the bending moment, parabolic bending moment diagram. Here we say that the critical section is at the support. In case of simply supported beam, it was at the center, whereas in case of a cantilever beam, it is at the support. It is of Hogging in nature with tension top and compression bottom, and its formula is also WL square by 2. So we will equate MUR to MU max. MUR is 78.21 and this is WL square by 2 MU max. So WU into L square is 1.4 square. The span is 1.4 meter span of the cantilever and upon 2. So this will work out as WU equal to 79.81 kilonewton per meter, and this will be further divided by 1.5, which is the partial safety factor for load, and this will work out as 53.21 kilonewton per meter. So the ultimate load is this much, and the working load when divided by 1.5 is the load factor, or the factor of safety for load as 1.5, will get 53.21. So these are the two values. So the actual value of load by which you can load this beam, this UDL, this will be 53.21 kilonewton per meter. So we now sum up the total answers of the problem. Only two things were asked: ultimate load and working load carrying capacity of the beam. So MUR we required, we had to calculate MUR, but we did not mention that in the final answers because that was not asked in the problem. So these are the two answers, WU and W. So friends, with this we have covered two problems of flexural analysis. Both of the problems were having some different aspects, and both of the problems together will clear all the concepts of flexural analysis. Now before we proceed further, we have to have a formative evaluation, which is a self-test. So pause the video and write on the paper the answers of the following question. There is only one question. A rectangular beam. This is a complete numerical problem which is similar to the problems we have solved in this video. So just solve this entire problem. A rectangular beam has effective section as 230 mm by 450 mm. It carries bottom reinforcement as 2 bars of 20 mm diameter plus 1 bar of 16 mm diameter. Materials M20 Fe 500 grade. Span of the beam is 4 meters simply supported. Determine two things: A, ultimate moment of resistance, and B, ultimate and working load carrying capacity of the beam. Now this is an application level of problem. So do solve this problem fully. If you have taken down the problem, we will proceed for the next slide. So friends, this is the time to sum up. We are at the end of this video lecture. We have seen two numerical problems on flexural analysis. We started with expected learning outcomes as to determine ultimate moment of resistance of given beam and to determine ultimate load carrying capacity of given beam. We had two problems in the contents of the video lecture. Numerical problem 2.6.1 on simply supported beam and 2.6.2 on cantilever beam. Check whether you have really understood and you are able to solve the problems. Now we use some key terms in this video: moment of resistance, load carrying capacity, balance section, under reinforced section, cantilever, over reinforced section, neutral axis, ultimate load. So if you have any doubts left or queries left, contact your teacher. You have to solve the summative assessment quiz, which as usual I am giving in the form of Google quiz. The link of this Google quiz as usual is given at the bottom of this video in the description section on the YouTube. So do solve this summative assessment quiz and check yourself. Now our best friend Smarty has come again to give us thanks. So thanks for watching this video lecture and have a good time till we meet again.